Well, that's the argument I give on the next page, all right? So this...
It's injective, but I thought for it to be invertible and like that it had to be bijective and onto. Nah, you get invertible maps that are also one-to-one.
Yeah.
I might be messing up my definitions.
No. I mean, for it to be invertible, we also need that it's onto. Now, it could just be I missed the word onto here in my... Let me just take a gander here. We're in section... come on. 6.4 or 5? 4 at the moment.
Yeah, it has to be injective and surjective.
Isometry is a one-to-one mapping. Oh, onto. Yes, I missed that onto. That onto is important. Thank you. Very good. You're right. And surjective. Yeah, you're right. Without that condition, for sure, the inverse wouldn't necessarily exist. But if it's a bijection, right?
Yeah.
In other words, so f of m is equal to m bar. To prove that the inverse map is an isometry, all we would need is that, the push forward of the inverse map also satisfies this condition. And you can prove that. So it turns out that if you have an isometry of surfaces, then it's, it's a bijection which preserves the dot product for the tangent space. And through some elementary calculations, the inverse of such a map is also such a map. So it's a very nice kind of thing. Now, that's actually not what we're primarily interested in this section. But the next proposition is like, if you have two isometries, then the composition of two isometries of surfaces is again an isometry of surfaces. All right. And then the next proposition is that the inverse is an isometry, which I just claimed. So like the next page has the calculations to support what I was just claiming. All right. And then the theorem on page 3 of my lecture 20 states that isometries preserve intrinsic distance. All right. So like.
We learned that already, though, right?
Well, we learned it before for.
Because it was like P and Q, then you push forward it twice to something else, and then it should be the same distance, right?
Right, but that was for that was specifically for rigid transformations.
Okay.
And these are not rigid transformations. These are much more malleable, as we'll see. So, but the next property is that an isometry preserves distances in the following sense. Let me draw a picture. So like, if this is M, and over here is M bar, right? And you've got a curve, alpha, and it connects, say, point P to point Q in M. And then you've got an isometry of surfaces, F here, all right? And it carries alpha over to what we might call alpha bar, which is F composed with alpha. All right, so alpha bar, it's a curve in M bar. It goes from F of P to F of Q. All right. And in fact, you can prove that I think the theorem actually is that the length of alpha is equal to the length of alpha bar, really. And so, like, what's the length of alpha bar? How are you going to calculate that? So, I mean, let's suppose that, alpha goes from where to where. Let's say, T1, T2. So to calculate, and so the same for alpha bar, its domain time would go from T1 to T2. So to calculate the length of alpha bar, we would integrate from T1 to T2, right? The length of alpha bar prime at, say time t, dt. But that is what? Integral from T1 to T2 of the square root of, alpha bar prime dot alpha bar prime. But here's the thing. The push forward of alpha prime is equal to alpha bar prime. That is a definition in our current notation of the push forward. It says that you take the derivative here and you map it to the derivative of the corresponding curve over here at the corresponding point. That's one of the definitions of push forward. So this is straight up the push forward of alpha prime dot the push forward of alpha prime. And what do we get to say about that? Remember, we're assuming that F is a isometry of surfaces, right? Which means that the push forward of alpha prime dot the push forward of alpha prime is just alpha prime dot alpha prime again. And that is nothing more than the length of alpha. And then, of course, this stuff passes through the whole inf length construction, right? If it's true for a curve, it's going to be true for the infimum of all curves that connect 2 points. So isometries of surfaces maintain the distance between points on surfaces.
So why couldn't we just, well, I guess since it's not rigid.
So I say isometry can be thought of as bending a surface in such a way that the distance on M is maintained. The preservation of the dot product from TPM to TF of PM bar also preserves angles between curves. So an example of, I would say that, the process of taking this, all right, like if you want to think about mapping this paper, right, to this thing, well, I would say that's an isometry, but I can't quite say that because when these papers, when they join, then I'm in trouble because it breaks the, what does it break? Curses. The one-to-one.
Yeah.
Yeah. I mean, so you can't get from here to here and still have a mapping of surfaces. However, this, like that, is what's called a local isometry. A local isometry is a mapping of surfaces, right? Which means that it's a differential map from one surface to another, in the way we talk more and blather on and on about in Chapter 4. It's a mapping of surfaces that preserves dot products of tangent vectors. All right, and that's what a local isometry is. So the difference between isometry and local isometry is what?
You use the local to figure out what you want.
Yeah, I mean it's basically this. We put local here, and we lose this bit.
Yeah, because it's just, wait.
It's just a mapping that preserves dot products of tangent vectors.
Okay.
Now it is true that this condition,
Well, if they don't overlap, if the local isometry doesn't overlap, it keeps its one-to-one. No, it doesn't, because it's a certain no.
well, okay, so
No,
this,
'cause you could have two
the example we were just looking at, that's the
Yeah.
global. So like globally, you can fail to U101, right? But if you restrict such a mapping locally, if you restrict it down enough, you can always restrict to a one-to-one map. In other words, let me just break it down a little further. This condition implies that the push forward or the differential is an orthogonal transformation, which means that it's an invertible transformation. There's something called the inverse function theorem. The inverse function theorem says that if you have a mapping of surfaces where the differential is invertible, it follows that the function can be made injective by suitably restricting it.
Yeah.
So,
You could do that, yeah.
yeah. Now, there's more. So we have that, and so if we had a local isometry, this still holds as long as you don't get as long as you don't run into the problem of the curve looping back on itself, right? So ignoring global issues, you still have preservation of like local distances, but you got to be careful about like the global aspect of the map ruining the closest distance between 2 points, right? But there's more. So what else can we say about a local isometry? And this is what the lemma here says. Lemma 4.5. If we have f from M to M, mapping of surfaces, which in O'Neill means that the function is differentiable, a differentiable function from M to M, plays nice with the coordinate maps there. Then for each patch X going from D to M, consider X bar going from, well, X bar equal to F composed with X. That's going to be a mapping from D to N. Then, given this setup, all right. So we're talking. We have two surfaces, all right. Let me draw the picture again. So we have M. Over here we have N. We have this mapping F going from here to here. What's that? No. We have this patch over here, X, and we have a patch over here, X bar. And X bar is built in a specific way. It's built by transporting the patch on M over to the patch on N through the surface map. All right? So given this setup, something very neat happens. Then F is a local isometry if and only if what? For each patch X, we have E equal to E bar, F equal to F bar, G equal to G bar. Now, so what do we mean by E bar, F bar, G bar here? What's that mean?
Isn't that what we did before? The
EFG, right. So what is, so like E bar, for example, means X bar U dot X bar U.
Yeah.
But that means F composed with X, right, u dot f. So the thing is, and getting to the point here, x bar u is literally the push forward under f of xu. And the push forward under f of xu. And okay, so if this is, on the other hand, E is equal to what? Well, xu dot xu, right? So what does it mean for E bar to be equal to E?
That they have the same H and K? No, was it? Yeah, right.
I mean, well, we have on the one hand, we have E bar is equal to this. On the one hand, on the other hand, we have E is equal to that. So if these two are equal, right?
That means x bar equal?
That means that this and that must also be equal, right?
Yeah.
But what does this and that also being equal say about f? F is a what?
One-to-one function? No.
No?
It's identity function?
It satisfies the local isometry condition.
Oh.
It preserves the dot product with the push forward.
Yeah.
So that's the proof of this lemma.
Yeah.
And you can do the same calculation with the f bar and the g bar. So wait a minute. So a local isometry, it preserves distances between points. It preserves the warping functions, right? What else does it preserve? What else do we transport with a local isometry? On page 6, I'll probably come back to this example, like, maybe start a next class. I'll do this one maybe. Because the examples in here I have to be more awake for. Examples are hard. All right. He also defines, he has this throwaway comment about conformal maps at the end of the section. I don't really care, whatever. And that brings us to 6.5, which is the intrinsic geometry of surfaces. And so I'll read the preamble here. An isometric invariant, all right, is a concept preserved by isometry. So we've already seen that distance between points is an isometric invariant. We've also seen that the E, the F, and the G are isometric invariants, right? Is that fair? Are they invariants? Yeah, I think that's right. So, in other words, what we're interested in is deciding what of the concepts, the shape operator, the omega ij, the coframe, theta I, the adapted frame ei, the unit normal u, which of these belongs to the geometry of M alone? All right, like, see, because essentially this is the idea that these local isometry, it only captures the local geometry of the surface. So if something's part of the local geometry of the surface, then a local isometry should preserve that, whatever that is. And so let's see what it does. Lemma 5. Wait a minute. Oh, yes. Okay, so lemma 5.1. Well, we already have lemma 5.1. The connection form omega 1, 2 equal minus omega 2, 1 is the only one form that satisfies those equations. All right, so yeah. I think we already know that, right? We actually worked that out already today. So write it up here. So we already know that. D theta 1. I suppose that it's the only one form which satisfies these equations. Maybe that's something that we haven't actually proven carefully, but it's awful close to what we proved. I mean, maybe we did it. I don't know. All right. On the next page, I encourage you to free your mind. And by that, I mean that we can define, I'm turning the tables here. I'm suggesting instead of using the covariant derivative to define the connection forms, that we could instead define the connection forms using the structure equations. So we're making a new definition, if you will. Definition. So what that means is going forward in this section, we're only allowed to use this to show that this idea is self-contained. All right, that's what's meant. So definition, omega 1, 2 of E1 is d theta 1 of E1, E2. And omega 1, 2 of E2 is d theta 2 of E1, E2. All right, and then extend linearly. Do you know about this? Extend linearly? If you define a linear transformation on the basis, then you can extend linearly, right? Like if I told you, you know, omega 1, 2 of like A E1 plus B E2, what would you do? You just do, well, A times omega 1, 2 of E1 plus B times omega 1, 2 of E2. That's extending linearly. You know, you already know what the values omega 1, 2 of E1 and omega 1, 2 of E2 are. So you can do it. All right. I say, remark, omega 1, 2, as defined above, satisfies the structural equation by lemma 5.1. It's by lemma 5.1. This is lemma 5.1. So what is I say? Omega 1, 2 satisfies the structural equations. Yeah, okay. I mean, if we, I think all I'm saying is that this and that are consistent. And right. I mean, all that's missing here is going back into the expanding into components and working out how the components works. Like this would expand to omega 1, 2 E1 theta 1 plus omega 1, 2 of E2 theta 2, and then I'll get wedged with theta 2. Well, that just drops back down to theta 1 wedge theta 2 and omega 1, 2 evaluated at E1. Well, that's what's here, omega 1, 2 E1. And that would be the coefficient of d theta 1, that'd be the coefficient of theta 1 wedge theta 2, which incidentally would be what you get when you, the thing that I haven't written down today yet is this, theta 1 wedge theta 2, when you evaluate that at E2 wedge, E1, E2, well, that's just 1. All right. And that's the part of chapter 4 I didn't talk as much about. All right, so let me get to the point here. So we're thinking about, we have a surface M, we've got another surface M bar. We're taking our frame, adapted frame here, E1, E2, we're taking a local isometry F. Well, we're taking a map F. I think it's going to be a local isometry. And we're pushing these over here to E bar 1, E bar 2. All right, so like F star And again, you're right, this does feel like chapter 3, it really does. But the difference is that now we're on surfaces. So like, these are vector fields on a surface. We're pushing them to another pair of vector fields on the surface that are, you know, and my claim is that, well, the next claim here is that if you have an adapted frame here, and you have a local isometry to another surface, then the push forward of an adapted frame is an adapted frame. And the proof of that is really pretty simple, because f star of EI dotted with f star of EJ is what? Yeah, it is, but why is that? That's because this is EI dot EJ, right? Because it's a local isometry. We're assuming it's a local isometry. And then, like you said, that's Kronecker delta IJ, which says that the fact that this is a local frame gives you that these guys are also a local frame. So, adapted frame, push forward to adapted frame. But there's more. There's more. The other thing that's very nice is that the theta 1 is the pullback of theta bar 1, and theta 2 is the pullback. So now the star is upstairs, guys. So I'll try to talk more about this like next time we meet, because I haven't done it much yet. I mean, we bumped into pullbacks like a while ago, and then I kind of like said, let's come back to it later. Later's next class. So pullback, if you have a differential form in the range of a function, you can do the pullback of the form and bring it back to the domain. So the pullback goes opposite the push forward.
Why is it not just an inverted?
It's just the way it works out. We'll talk more about it next time. But so if you, this is pretty cool, because once you have the adapted frame over here, then you get the co-frame, you know, theta bar 1, theta bar 2, right? Mm-hmm. And what I'm telling you is that the pullback, which is a standard math thing, the pullback of the adapted co-frame is the co-frame of the original thing. So you transfer, you push forward the adapted frame,
and you can take back the co-frame.
Yeah, you do the usual construction of constructing the co-frame to the adapted pushed frame, and when you pull that back, you get back to the co-frame. So everything links just like you want. E is equal to E bar, F is equal to G F bar, G is equal to G bar. Everything is pulling, and there's more though. The 1-2 connection form is the pullback of the 1-2 connection form over here. So it's not just the adapted frame and co-frame, it's also the connection coefficient.
So the only thing that's missing really from like being a true isometry is just that it's non-differential points.
Yeah, well, that it's not bijection.
Yeah.
Yeah. And that's it. So, and then what does this say? So how did we define, how was the Gaussian curvature related to all this stuff? Remember?
It was K was equal.
We were at D, what was it, D omega 1, 2 is equal to
D omega 1, 2 is equal to D cosine phi.
Oh, no, the abstract formula.
Omega.
Is it minus K? Theta 1 wedge theta 2, I think.
D omega 1, 2 is equal to omega 1, 3 wedge omega 2, 3. Oh, you're talking about the Gaussian though.
Yeah, I know, there's a lot of different ways to skin a cat. Right. And so if we write Gauss's equation on m bar, right, what is it? D omega bar 1, 2 is K bar, and then, you know, bars and everything, right? thing is, this, let's see how to argue it nicely. Well, I mean, I have written this, d omega 1, 2 is equal to d of the pullback of omega 1, 2 bar. And then the cool thing about the pullback is it it commutes with the differential. So like that's the pullback of the differential of omega bar 1, 2. But that's the pullback of k bar theta bar 1 wedge theta bar 2. And that is f composed with k. That's the pullback. When you pull back a function, it's just composition. And then we get pullback of theta bar 1, which is theta 1, and the pullback of theta bar 2, which is theta 2. And in other words, that's equal to k. And I think I needed a minus here and here, and there's still a minus here. But that's minus k theta 1 wedge theta 2.
Which is what we got in the first one.
Right. Well, anyway, I guess I should just write that f star. Okay, but anyway, the point here is that the Gaussian curvature is the same as, basically k is equal to k bar with the proper interpretation. So what does that say? That says that a local isometry preserves distances between points, it preserves the warping functions, and it preserves the Gaussian curvature.
So what does it not preserve is the question.
Extrinsic geometry. And so this is Gauss's theorem egregum, or his awesome theorem, is that the Gaussian curvature is an isometric invariant. So explicitly, if you have a local isometry, then the Gaussian curvature is preserved. Now, Gauss did not do it in the way we just did it. When Gauss did it, it was like a battle of the, it's all in terms of the alphabet soup stuff, the E, F, G, blah, 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 blah. But,
he brute forced it.
Yeah. I mean, basically we're proving it using push forward and pull back idea. Now, so some comments. The equation d omega 1, 2 equals to minus k theta 1 wedge theta 2 shows that the Gaussian curvature can be calculated without knowledge of the shape operator. Omega 1, 2 does not have anything to do with the shape operator. Remember, the shape operator depends on the other connection coefficients, the omega 2, 3 and the omega 1, 3, right? Omega 1, 2 doesn't have anything to do with shape operator. On the other hand, the Gaussian curvature is the product of the principal curvatures, right? Mm-hmm. And the principal curvatures are eigenvalues of the shape operator. They are very much tied to the shape operator. So you have to understand this idea that the Gaussian curvature is independent of the shape operator. I mean, there's this delicate balance because the Gaussian curvature is an isometric invariant, right? And yet it's still the product of the principal curvatures, which are very much extrinsic. And when I say extrinsic, I mean it depends on how the surface is situated in space. So let's see here. How can I say it? So the mean curvature of a plane, 0. The mean curvature of a cylinder,
0.
Is it still 0?
The curvature of the thing was 0.
The mean curvature.
I don't remember.
I think the mean curvature of a circular cylinder is minus 1 over 2r. Right. See, the mean curvature depends on how that surface is the shape. What we can see is the shape of the surface is the language he uses. The shape of the surface in R3 is different for this and for that. But they're both flat spaces because they have Gaussian curvature 0 which determines the local geometry, how distances between points are determined, on the surface itself. So I say the term flat is from the intrinsic perspective. To the inhabitants of the cylinder, the geometry is the same as if they lived on a plane, at least locally. Of course, on the cylinder, you could walk from your home and then back to your home again without ever, turning back. Because globally, there's a difference there, right? But another application, a sphere with curvature 1 over r squared, as we calculated today, right, cannot be isometrically mapped to the plane because the plane has Gaussian curvature 0. So you cannot preserve the local geometry of the sphere and map it onto the plane.
Oh, yeah.
Because
we do that all the time with
Gauss,
maps.
because the Gaussian curvature is 0 for the plane, but it's 1 over r squared for the surface. And we've just proved that if you have a map which preserves distance locally, you also have to preserve Gaussian curvature locally.
Oh, is that principle inherently why maps suck?
This proves maps suck. Yes. This proves that the job of the map maker is non-trivial. Yeah.
We proved this really late in map making.
Right. So it becomes a very interesting question then to ask, given two surfaces that have a different shape, right? Are they really the same geometry and just sort of embedded differently? This becomes a meaningful question. Like,
is the hill the same as a flat?
Mm-hmm. And so one of the most interesting examples of this is, the example of the helicoid and the catenoid. And there is so the helicoid is, I've tried to draw some of that in the videos, right? But anyway, maybe next class we'll start with that. I need a projector for that. So anyway, thanks guys. I appreciate your patience.